What's up, the YouTube kids? Chemistry, that's what's up. Hey look, remember we had some ice and we melted it. And then we recorded the temperature of the ice as it changed from ice to water. And then as that water then changed from liquid water and boiled and then turned into a gas. And we got a graph that looked like this. Basically, this is the melting was occurring, right? And then as soon as we had all liquid, the temperature shot up. And then our temperature stayed right here at 100 while it was boiling. Now we know that latent heat is here and here. And we know that the graph is flat, or this latent energy is the energy that is used to change the phase. So here's the last thing. This is the last part of the ice lab. And that is, if we did this over a long period of time, which one of these lines would be longer? Would the melting line be longer? Or would the boiling line be longer? Okay? Now the thing is, it takes a different amount of energy to melt ice than it does to boil water. It's two different amounts of energy. So the graph will either look like this, with a shorter line for melting and then a longer line for boiling. And that's if it takes more energy to boil than it does to melt. Or it's the opposite. If it takes more energy to melt ice, the line will be longer, then the boiling line will be shorter. See the difference in the two that I just drew? So one of these is going to be true. And you can make a really reasonable prediction, a really good prediction, just by looking at your tables. Page 1 of the North Carolina Chemistry Reference Tables has a lot of information about water right here in the middle. We have a term called the heat of fusion, another term called the heat of vaporization. We also have the specific heat of water, okay, the specific heat of liquid water. And the specific heat of water is ice, the specific heat of water as steam, and the specific heat, which is really high, for water as a liquid. And these are joules per gram, all right? And I know we haven't talked about joules much, but joules are energy. And joules are a way we can measure the energy that's coming out of the hot plate, okay? Up here we have the heat of fusion of water and the heat of vaporization of water. And I'm purposefully not talking too much about this stuff because I want you to make your own assumptions and your own guesses, okay? So you're basically going to have a choice. Which one of these graphs do you think is the most accurate? From looking at the information we just looked at, graph A, or do you think graph B would be the most accurate, okay? And these are different, and you should understand why they're different right now from just what I've shown you. Let's take a look at this very simple, not perfectly scientific, but pretty darn scientific experimental setup. So what we have are 100 grams of ice, and that's right at 0 degrees Celsius. And I've got 100 grams of water, and it's going to be heated up to 100 degrees Celsius, or right around 100, before I hit go. In other words, these are going to both be right where the latent energy would be impacting your graph. This is going to be the lower flat part of your graph, the melting part, and this is going to exhibit the upper flat part of your ice melting graph. This is going to be the boiling part, right? Now, if we watch these and we watch the stopwatch in the background, determining which takes longer, melting all of this ice or boiling all of this water, or tell us which part of the graph should be longer, right? Okay, we're right at the boiling point, right at the melting point. We're going to start our stopwatch. And we've just turned on this ceramic heater, and we're going to have to assume that these heaters are the same. Now, don't worry. I'm not going to make you sit here and watch ice melt and water boil for a long time. We'll pause. So we're a little over 90 seconds into this. We have a raging boil, and you can already see we've made some advances in melting our ice. What is another word for boiling water? That's right, vaporization. What is another word for melting ice? That's right, fusion. So let's look on page 1 of our tables. Now, as your tables magically fall out of the sky, let's take a look. The heat of fusion of water, that's 334 joules of energy per gram. The heat of vaporization of water is 2,260 joules per gram required to vaporize water. So, which of these two are you expecting to take the longest? The boiling or the melting? Let's watch that clock in the background. Okay, we're 5 minutes into this. If you look, there's just barely any ice. And I'm going to tell you right now, as I was talking to you, the ice is gone. So all of the ice is melted, and it took it right at 5 minutes. Now let's think about our numbers. Let's think about the numbers for fusion and the numbers for vaporization. What guess would you make if you were making a guess? At what time, if the 100 grams of ice had melted in 5 minutes, at what time do you think all of this water will have vaporized or boiled? What time on the clock? I haven't exactly taught you this, but I do absolutely expect you to infer this and make a good guess. And your guess may not be what actually happens in the real world, because these hot plates could be a little bit different. We're assuming they're the same. But your guess should be a very scientifically reasonable hypothesis. Just checking in on our progress here at about 9 minutes. This water started boiling, so I cut it off because we're not measuring it anymore. We already know that the 100 grams of ice melted in 5 minutes, okay? We're watching this. And if I'm looking at the level, of the water, I tell you that there is around half of it left. There's about half of it left. Okay, so we're already done here. It only took around 15 minutes for all of this water to boil out. Now, when you were making a guess, you should have guessed that it would take about 7 times as long. So you should have guessed about 35 minutes. And honestly, I was expecting it to be longer. So several things could have happened. What are some reasonable flaws in this experiment? Things that could easily flaw the experiment because it wasn't that scientific. Okay, I'm going to give you a question about that, and I need you to pick 2 of them, the 2 of these that are reasonable flaws in the experiment. And I hope you enjoyed this as puzzle. Peace out. So in the end, with everything you saw, even with the flaws, it was obvious that one of these is the more reasonable graph. So again, in the end, I'm going to ask you which one of these was the better choice.